All right, guys, I'm going to go ahead and get started. First of all, welcome. Good to see you all again, or not see you all again. If you want to turn on your video, that's awesome. I love it when you do. But anyway, it's good to be back with you again. To start off today, I just wanted to double check and make sure everyone I was looking at the test scores and kind of going over the test. And so it looks like there's probably a few of you that still haven't taken it. So first off, I would just encourage those that haven't taken the test to um, get on there and get it taken. Again, I don't do due dates, but because I know your life's busy, but if you can try to keep up, that's the best way to get through the class. So just a reminder of that. So get the test if you haven't done it. And then also, it looks like we had pretty good scores. Again, kind of a pretty average bell curve, but it looks like we had some people as high as 38, and then it's probably a little higher than that considering the uh, messed up question that we had. So hopefully, and that's the other thing I want to touch. Hopefully, all of you got the email I sent out. One of the questions got through that was incomplete. And so I wanted to just briefly go over that. So those of you that haven't taken it yet, you may come to a question that has some incorrect information. Look at your email, but essentially the question on the test was what is the half-life in hours of a material whose activity after 4 hours was found to be 9.46 millicuries. And as many of you discovered as you tried to figure out what was going on with that question, you realized that we're missing some information. If we're going to have a missing half-life, then we have to have at least an original activity and an activity to be able to figure out a half-life. But you were missing half-life and you were missing your original activity. So for those of you that just struggled through that and probably felt like you wasted your time, I apologize for that one getting through. But at the same time, you probably are that much better at these. I think the fact that a lot of you saw that and said, hey, I can't do this test, that shows me you're understanding how to do these problems. So good for you. Like, even though that might have been a pain, I think that in some respects, we can look at that as a good learning experience. So, but I apologize that that test question slipped through. It shouldn't have. Um, the missing amount, just for those of you that haven't taken the test, so it'll give you the activity, which I mentioned was 9.46 millicuries. And the original activity on the question should have been 15 millicuries to get the correct answer. Then you can figure out the half-life. So any of you that haven't taken it, just take a note down. It should be 15 millicuries. If you took it and got it wrong, I'm going to go back once everybody's done and I'll correct those answers and give you credit for that question. I would love to just be able to go in and change the test as soon as I figured it out. But when some people take the test, it kind of sets things in stone. And then if I go back and change, it can kind of mess up scores and stuff. So I'll get you the credit you deserve. So sorry about that. Thanks for suffering through that with me. Yeah. And then on the coming test, I I had originally had it available today. I'm gonna make it available tomorrow. I want to just double check that test one more time before I send it out. So you'll be able to access the test for this lecture tomorrow. But I'm going to go through that right after we do this lecture and just make sure there's not any weird questions on it. So, okay. All right, we are going to go ahead and get started. So let me get my slides pulled up and everything arranged on my desktop here. All right, can you guys see my slides? Okay, seeing some head nods. Thank you. Perfect. All right, as always, you guys interrupt me if you have a question, if there's an issue. I love to be interrupted because I love questions. Today we're going to talk about radiation detection equipment. Last class we kind of focused in and honed in on the gamma camera, which is something you use a big percentage of the time in nuclear medicine. Today we're going to cover some of the other equipment, the ancillary equipment that we use. And then at the very end of this, we also are going to need to have a talk about statistics. So we're going to have a little section at the end where we go cover statistics and why statistics are important in nuclear medicine. And hopefully I can keep from boring you guys to death during that section. So, all right, let's get started. Okay, so these first few slides you're going to recognize because they're actually a copy of the slides that I did last time. Radiation detection, kind of the basic principles that you learned at the first of our last lecture, are going to be the same. So I included them here. I'm not going to go over them again in detail and make you listen to me lecture on them again. But I put them here so that when you're looking at this and when you're studying, you can realize that a lot of the principles, the basic principles that applied to radiation detection for gamma cameras are also going to apply today to the things that we'll talk about. And so I've included those on here. And so I'll probably just kind of briefly skip through some of these slides. We'll keep these here. I won't say much. I'll stop here. Again, last time we covered gamma camera. So today we're going to cover the rest of these. We'll talk about dose calibrators. We'll talk about GM survey meters, ionization chambers. I'm not going to specifically cover surgical probe, although you'll notice that these four up here are all gas-filled detectors, so they all function generally the same way in basic principles. So we'll look at these first three in more detail, and then a surgical probe essentially just functions the same way. Then we're also going to talk about thyroid probe. We'll talk about the well counter. So we'll cover those today in our discussion. All these properties, again, that we talked about last time are going to be similar principles. So all of these detectors that we talk about today, we'll think about things like efficiency and sensitivity. Those principles of geometric, intrinsic, and photopeak apply. Resolution applies again, although we'll talk about energy and temporal resolution apply, but not necessarily spatial, right? Because spatial has to do with getting an image on a camera. And the things we're going to talk about today, we're not creating images, we're just trying to detect radiation. So that's maybe the one difference that will change from these basic principles. So remember when we talk about efficiency that we're talking about of the number of events detected, how many of those available events can we actually see and we can get, right? So that's our sensitivity or our efficiency. And we have geometric, which is we have to be able to see them, intrinsic, photopeak. So we'll talk about some of those same things. Remember when we talked about geometric last time, a lot of that was, I mentioned the size and shape of the detectors. And most of what we talked about last time was our gamma camera. So it was a single detector above us. We talked about like source to distance, but today we're going to talk about the well counter and this idea of, remember I said if something's completely surrounding a radioactive source, that would be the most sensitive thing. But most of the time we can't get that. And we'll talk about a well counter and how a well counter comes close to being that most sensitive thing. Intrinsic, again, is how much of the gamma photons can we actually get. We need to be able to stop these or sense them or detect them in some way. So we'll talk a little bit we'll reference that a little bit today. Again, I included some of these other slides to remember the photoelectric effect. And then let's see, the other one I wanted to show you or talk about is energy resolution, the ability to see something. Temporal resolution is an important one we'll talk about today. So this is, again, the conversion of a signal from energy or radiation to some sort of electronic pulse that we can measure. And last time I referred to, and we didn't talk as much about this with a gamma camera, but we'll reference it more today, and that's dead time. And so remember, dead time is the time that it takes to go from that signal or that radiation all the way to that electronic pulse. And we talked about how there's kind of a couple of forms. There's non-paralyzable and paralyzable. And so the paralyzable, again, is an event takes place or there's a detection that happens, and then that process goes all the way through to the electronic pulse without interruption. That's non-paralyzable. And then paralyzable is where the system sees an event, but if another event happens, it starts back over and goes to that initial event. So we're going to reference that a little more today. And that, again, that idea is that dead time. How long does it take to happen? And remember that I talked about last time that when we do talk about dead time, we're not talking about long periods of time. We're talking nanoseconds. So, 40, 50 nanoseconds, something like that. It's a very quick time. It's not something we necessarily perceive ourselves, but that it's occurring. Okay. And then again, system resolution is not necessarily what we're going to talk about in terms of detail on an image. Okay. So we're going to start off by talking about gas field detectors. Let me grab. Sorry, I had a window pop up in my way. Okay, so with gas field detectors, I mentioned a minute ago, we're going to talk about GM meters, we're going to talk about ionization meters, and we're going to talk about a dose calibrator. So that will apply to all of those. And this would apply to a surgical probe, like I said, we won't mention. But I'm going to cover kind of the basic principles of how they work, and then we'll get a little bit more specific on what the difference between it being a GM meter or being an ionization chamber, and then get specific on the dose calibrator, okay? So here's how this works. Any gas field detector, you essentially have a chamber, and that chamber is filled with argon gas. Okay, argon gas is a pretty dense gas, and within that chamber, you then have a cathode and an anode, right? So familiar with X-ray tubes and a lot of other things that are electronic, you have a positive side and negative. Negative is your cathode, positive is your anode, okay? This creates a circuit, and there's a voltage applied across this circuit. So what happens is when a gamma ray, any kind of electromagnetic radiation, comes in and it strikes the argon gas. What happens is when that strike happens, it ionizes the argon gas, and you get a separation of an electron coming off, and then the argon gas molecule which is left. And we're going to call that an ion pair, okay? These two things, an ion pair. So the ion pair and the electron. So you get the separation of those two things. Now electrons, as you know, are negatively charged, so they're going to be attracted to the cathode. And then that ion pair with that negative coming off of it is going to be attracted to the anode, okay? Or I said that backwards, sorry. The electron's attracted to the positive anode. The pair is attracted to the negative cathode. But you get that attraction and you get that separation. Now, that separation happens because you have a voltage across the line, right? So you have a voltage that pulls those apart. Very similar to in the X-ray tube where you have some thermionic emission, you apply voltage and it goes across and creates our X-rays, right? So this is the same idea. It's pulling those two things in separate directions once that reaction happens. And so that's kind of your basic principle. And the idea is that the more gamma rays that it sees coming in, and the more ionization occurs, the more that those separate. And so what happens on your meter then when the voltage is applied is you get some kind of reading on your meter, okay? So the more that it sees, the more ion pairs are created and the more read you're going to get on your meter, okay? And that's kind of the basic thing that happens. Now, I mentioned that there's a voltage applied across, okay? And so what happens is we're going to see, and I'm going to go to the next slide, but we're going to see that we have the ability to increase the voltage. And as you increase the voltage, you're going to get more and more of these pairs created. And so we end up with this curve. And I'm going to go to the next slide and kind of walk you through the curve and then show you how this works. So this stuff is just kind of what I just mentioned there. Okay, so if we took and we said, okay, our voltage starting at 0 and then our voltage working up, and within the chamber, how many ion pairs are collected based on that voltage? That's what this is. So again, our x-axis is voltage, y-axis is ions created. So what happens in the system as radiation comes in, if we have our voltage really, really low, as radiation comes in, it'll strike and it'll create that electron and that ion pair. If the voltage is low, what will happen is there's not enough pull to pull those things to the cathode and the anode. And what will happen is they will simply split from the reaction and then they'll actually recombine. And so initially in this gas ionization curve, we have what's called the recombination region. Okay, so again, reaction happens, they separate, but they come back together because there's not enough voltage. Well, as you increase the voltage, that's how we begin to get reactions that we can measure. Okay, so the next range that you'll need to look at is this saturation range. Now, there are some books and things also refer to this saturation range as the ionization range. But it's called the saturation range as well, okay? So you have this middle range. What's happening in this range is that you get separation and there's enough voltage that it attracts those ion pairs and the electron to the cathode and the anode. So you get this separation, and when that separation strike happens, you get a current in the system. And so when that current happens, that's what then gives you a reading. Now, two things that happen in the saturation region. One is that as long as it's detecting a radiation, it will create more ion pairs the more radiation that it sees, right? And so you're going to get more current with more radiation that you see, and it's going to give you a rise on your meter, okay? The other thing that happens here is it's not just based on the amount, but it's also based on the strength, right? So if I'm detecting tech coming in at 140 keV, or I'm detecting I-131 364, that's going to give, because of the strength of the photons, that's going to give a different amount of this ionization, right? So I-131 will ionize more than tech will ionize. So in this saturation range, what you're going to get is, again, a creation from the amount of radiation and the type of radiation, and it's going to create more or less of a reading. And that gives you, that's telling you there's more or less radioactivity in that area, okay? So that's the saturation range. So what I want you to think about in this saturation range, this is where we have what we would call an ionization chamber, okay? And that just means that this ionization is happening, this saturation is happening. We can get a measurement in this range. So if you have a meter, and let's say you're doing a treatment with I-131, and you need to measure your patient's rate before they leave, you're using an ionization chamber because it's giving you a measurement. It's collecting and gathering and constantly getting data and giving you a measurement, okay? And that's kind of a way to think about it. You're using something in the ionization or saturation range when you're able to actually get a measurement out of it, okay? So then what happens is as we turn up the voltage, we start to go through a couple other ranges. This one is called proportional. And all that it means is that as we increase voltage more and more, we're going to create more and more of the pull of those ion pairs. And so we don't do a ton in this proportional range. It's mostly the saturation range. But as you increase this higher and higher and higher, you get up to this GM range. Okay, so when we talk about Geiger-Muller counters, that's what GM stands for. And you're up in this GM range. And what happens here is your voltage gets really, really, really high. And when the radiation strikes and you get the electron and the ion pair, you start to get some really high velocity actions towards the cathode and the anode. So they just start traveling at a high speed, okay? I'm going to go to the next slide because we're going to look at what happens. That this GM reaction that happens is different than what happens in the saturation range. And this is what makes your meters different between an ionization meter that you're just using to get a rate and a reading, and a GM, which is used to detect like small amounts of radiation and an on and off. And I'll get more detail on that, but let's go to the next slide. Oh, you know what? I included just some examples here of different ones. So you've got like, we'll go to the next slide and we'll talk about that in the GM in a minute, but this is what you kind of see in the heads of your survey meters that you have. So these are all gas-filled survey meters. And so this is kind of your chamber on the inside, your gas chamber. That's what they look like on the inside. This one's called a cutie pie, and it's got a gas-filled chamber just kind of right in the head here. And so just as we're talking, I just wanted to give you kind of a visual picture that you can kind of look at and think about to kind of see what's going on inside, but they have that chamber inside. Okay, so we need to talk about what's called a cascade or an avalanche effect. And this is what happens in a Geiger-Muller tube or in a reactioner when we get the voltage up to a Geiger-Muller range. Okay, so we're going to follow this through. So this purple line up here represents the path of radiation coming in, right? So this radiation, whatever it is, it comes in, and you have a strike with one of the argon gas molecules. Now, this is the same reaction as what happens in the saturation of the ionization range, but essentially you just get that ionization. So you get the ion pair and you get the electron. However, remember I said that the voltage is really, really high in the GM. So we've got our voltage really, really strong. So what happens as soon as this reaction happens, the electron and the ion pair are pulled towards the cathode and the anode with such great force that along the way, they actually strike other argon gas molecules and they cause more ionization reactions. And that's what this represents here, is that struck, we had our original ionization event, and then as it travels again, it started to make more and more reactions. Oh, and by the way, I should have kind of said this at the beginning, but what you're looking at here, a lot of the tubes are set up this way. So what you have in the middle is your anode is right down the middle of the tube, and it's almost like a wire down the middle of the tube. And then the walls of the tube essentially become your cathode. And so that's what you're looking at here, is everything's being pulled, it's causing more and more reactions. And essentially you get this avalanche effect where, because the voltage is so high, almost all the argon gas goes through this process of being ionized, okay? Now, there's one other kind of reaction that occurs during this, is that so everything that travels is traveling towards that anode, that which is all the electrons, right? The electrons are traveling toward that anode and they're creating the reactions. But remember, the ion pairs are going to be pulled towards the cathode, right? And that's the wall of the tube in most of these. What happens is when that ion pair strikes the cathode or the wall of the tube, there's another reaction that's created. Now, in this case, it doesn't have an ionization reaction. It doesn't kick off an electron. But what it does is it excites the cathode. Remember last time when we talked about scintillation, and we talked about how you get this excitation within the material, and then when that excitation calms down, you get light off. That's exactly what happens here. You get this excitation, and then you end up getting ultraviolet light that comes off of the wall of the tube. What that does is ultraviolet light actually also has an ability to ionize argon. So not only are all the electrons going in and ionizing as they go along, but everything that then goes and strikes the cathode or the wall of the tube is creating that light, and that light is also coming in and ionizing. And so you end up with pretty much this process where all the argon gas goes through this process and it peaks out. And so what would happen in your machine is that you'd get a dead time that was pretty much forever, right? One radiation event would ionize the complete tube, and your tube would be out of use and done. It would be dead. And that's what we mean when we say paralyzable, right? So this event happens, it paralyzes, it can't get any more events, it's kind of done. Obviously, that wouldn't be useful if that's the full reaction and that's where it ended and that's what we had happen. And so there's something they do to these tubes, and they add what's called a quenching gas, okay? So this is not the argon gas, it's a different gas. Usually they add a methane gas, which is kind of a gas that essentially, I don't know if I wouldn't call it natural gas, but it's a methane type gas. And what that methane gas does, when it is struck, when the light comes off of the tube, the side of the tube, that methane gas will absorb it. So it doesn't cause an ionization, it doesn't do anything, it kind of just absorbs that gas. And what that does is that allows the tube to slow down its reaction and not have everything fired off and reset. It'll reset, right? So that's what we call quenching gas. That could easily be a test on your boards. And so if you get that question, just understand that methane is added to the tube as a quenching gas. What the quenching gas does is it stops the avalanche reaction and allows the tube to then reset, okay? So you have this avalanche reaction, tubes reset by the quenching gas. Now this whole process, like I mentioned, remember we said we had dead time, which is the process from when an event starts to when an event resolves or is finished, okay? And so that whole process, like I mentioned before, in these gas-filled chambers is in nanoseconds. So you're talking 40, it could be anywhere 40, 50, 60 nanoseconds. If you get your meter, sometimes on the meter you'll have, or on the head itself, there'll be a sticker. And a lot of times on that sticker, you can look and it will show you what the dead time is on it. You can look on there and it will say 40, 50 nanoseconds. If it's not on your sticker, and you're interested, you can get really nerdy if you want, like I do. And you can actually go online. And if you look up, a lot of these meters are made by a company called Ludlum. So if you go onto Ludlum's website, you can look at their different models and you can find the model that you have, or you could even just Google, if you look on the side of your meter, it'll say Ludlum 44-2 or whatever. You can look that up and you can find the manual. And if you go in the manual, it has, in fact, that's where I got these pictures right here, was from off of Ludlum's website and their manual. But it will have a section there that will show you the dead time, so you can actually look up what the dead time is on your meter, right? But again, keep in mind that it's very slow, or excuse me, very fast, right? This doesn't happen in any kind of thing that we can recognize. And so the other thing to think about with GM is GM, when you turn on, you can get your meter and you can turn it to audio and you'll hear that beep, 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 beep. So every beep that you're getting there, that is this entire event happening. If you're on GM setting, a lot of the meters will beep for anything, but on a true GM meter, when you have it on audio and that's what you're doing, you're getting that entire beep or that entire process happening every time you hear that beep, okay? And it's going back down to zero. If there's anything else I want to tell you on this slide, let's go to our next one. So here's what I want to now separate the difference between an ionization type meter that you're using and a Geiger-Müller, okay? Because really the only difference, it's a gas field detector, but it's the amount of voltage we're applying changes how it functions and reacts and what it does. So these are the kind of two things that I want you to put in your head, and their differences when it comes to boards, when it comes to testing, okay? So remember, an ionization chamber functions in that saturation or ionization region. It has proportionality, okay? Meaning more photons will give you more current, or type of radiation will give you more current, right? And so there's proportionality. There's no dead time, meaning that it doesn't have that avalanche. We can sit on something and we can get a reading. We can measure our patients that have their iodine treatment and see where they're at, and it will just sit there and collect and collect and collect what their dose is. These are low sensitivity for high radiation levels, okay? This can be sort of confusing. What I mean by low sensitivity is that something that's highly sensitive can see tiny bits of radiation, right? So these teeny little things we're looking for, think about things like your wipes or just small amounts of radiation that you're trying to find, little background radiation, whatever. So it can see it's low. I said that backwards. Sorry. Oh my gosh. It's low sensitivity, meaning that it's not sensitive, that it can do a high dose. So if you're measuring your I-131 patient, they have a lot of dose coming off them. And so it's going to be less sensitive so that it can see that high amount. If it was super, super sensitive, that high amount will just overwhelm the system, okay? And remember, you're going to get a rate. So they're not as sensitive. They're made for higher radiation doses, and it's for rate. So again, think anytime I'm needing to get a rate or a measurement on something, that's when I'm in that ionization range and using it as an ionization chamber. On the Geiger-Müller side, in the GM range, remember the voltage is so high that it causes that avalanche. A lot of times when you're using your survey meters and you're just getting a bounce, one at a time, you're looking for, again, these are very sensitive, so you're looking for low level activity, but you're not going to get proportionality. Like you couldn't sit on your patient and know how many MR per hour that they're going to leave the department, because it would be all over the place and you'd keep getting those reactions. When you have audio on, this is kind of the one that's always made the characteristic clicking sound with each photon event, okay? Now, like I said, what I want you to do is go and look at what you have at your work. As manufacturers have made these things over time, they've kind of combined them, and you can almost do both with one. Like there's a lot of meters, depending on the setting you put it on, that it ups the voltage, and now you're using it as a Geiger-Müller. And if you lower the voltage down, now you're getting a measurement and you're using it as an ionization chamber. So remember, that's why they're just both gas field detectors, but that's how you separate the ionization versus the Geiger-Müller. There's also some of them that, originally only Geiger-Müller counters would make the classic beep, 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 beep. Now they've manufactured them so that if you turn audio on your meter, it's going to make beeps almost no matter what's happening. So there's a little bit of confusion. So what I would recommend is looking at your meters. Go and see what you have. Talk to your techs. Again, if you can look on the sides of them, and it may tell you what type it is and what it is. Or again, if you want to just get down into it, you can look and see online. You can look up that meter and see what type of meter it is and how it functions and things like that. So there's a lot out there in actual practice, but for test purposes, these are the two separations I want you to make and the specifics about those separations. And then again, look at your other ones. When we do our quality assurance class in the summer, part of an assignment that you're going to have is to look at the different equipment that you have in your department and kind of go through some of it. And so you'll take a look at these then anyway. But if you want to look at them now and see what they are, just as you're learning this process, I would recommend that. So take a look, see what you think. Any questions on that? Okay. Let me see on the. Make sure there was nothing in the chat. Doesn't look like there is. Okay. So one other thing we need to mention here, to add to more of the confusion, is you can also have heads that are based on scintillation. Okay. And I would bet that a lot of the heads that are in your department could be scintillation heads. So a scintillation head is exactly like your gamma counter. So if you look at this graphic here, what you're seeing here is there's a crystal on the front, and then behind it, there's a photomultiplier tube and a preamp. Okay, so this functions exactly, it's like having one single photomultiplier tube with a crystal that you can carry around and detect. So these are also very sensitive, like a GM is sensitive, but they also can do proportionality because it can count the amount of counts that you're getting separately. This type of system, though, if it's overwhelmed by too much, by a huge radioactive source, it will kind of go into a paralyzed state in dead time, and it won't be accurate. If you have one crystal and you have so much radiation that there's just counts all the time, it'll get to a certain point where it's reading high, but you can't trust the accuracy because there's so much it can only do to a certain extent, right? Because it's just one crystal, and so. Again, it can be limited. You'll mostly see these type of meters for trying to detect small amounts of radiation. You could use this for your daily surveys, although you're probably using an ionization chamber for your daily surveys. But this is another meter that you may see. But again, I'm not going detailed here, but exactly like your camera, it functions the same way, but instead of getting to where there's a pixel on the screen, it just gives that electronic pulse, and that pulse is measured and reads on your meter. Okay. All right. Okay. So when you talk about quality control, these are always test questions with quality control on whether it be cameras or meters or whatever. So both the GM and the ionization survey meters are pretty much identical on the quality assurance. They have to be calibrated annually, and I would add in the scintillation detectors as well. All of these require the same thing, but they have to be calibrated annually or after any repair. Typically, the calibrations are going to be done by an outside source. So there should be probably a tech or maybe a manager in your department that has the job of making sure the meters get calibrated and taken care of. And they usually have to send them out. So you'll be getting meters sent out and mailed back once they've done the testing and calibrated them. But remember, again, for testing purposes, those have to be done annually, but you're not going to be someone that does that calibration. That calibration is done by usually a company. The calibration date has to be noted on the instrument. So again, if you look on the side of your meter, you're going to have a sticker, and that sticker is going to tell you the calibration date and when it's due. So it has to be done annually. Battery has to be checked daily. So typically on your meter, you're going to have a switch or a button that you can push, and then it will give you a reading on your meter based on the battery. Obviously, you have to make sure you have good batteries in your meters, because if you don't have batteries, you're not going to get voltage. If you don't get voltage, then you can't, that ionization reaction can't occur. So conceivably, you could think you were measuring, and if your batteries aren't functioning and they're weak or whatever, that could potentially mess with your voltage and you're not getting accurate readings. So usually there's again a button to check your battery. That is a daily check that should happen. And then each meter should have its own check source with an exposure reading at the time of calibration. So when they did the calibration, they put the date on there, and then they'll put the type of source that you have. And usually your source is a little disc or kind of a puck shape. Typically, it will be hooked to the side of your meter. It'll be connected, and they're really low radiation source. It's really small. Usually less than 10 mics or somewhere around them there, but it'll be attached to the side of the meter. On At some facilities, you could have them not attached to your meter. If so, they would be in the hot lab, I'm assuming, somewhere. And usually they're labeled so that you know which source goes with which meter, because they're specific. So you won't have like one source that just works for all your meters. It should be a source with every meter that you have. And so if they are separated, make sure you're measuring the right QC source every day to get a reading. And then again, if it's connected, that makes it a little bit easier. But that daily reading should be taken and compared to the calibration. Now, what a lot of you probably do in your sites is you get the reading and then you go to a computer and you have something that keeps track of all your hot lab QC stuff, and you go and you put a number in, like maybe your reading is like 0.02 or whatever on your meter, 0.05, whatever it is, and you put that in. And what's happening in that software is whatever tech is in charge of your meters, when those meters were received, he took the reading on the sticker that said what it should be, and he just put that in your computer software, right? And so that's how it's checking. But what actually is happening is there's a reading